This conference will now be recorded.
So, very good evening, students. Today, we'll be discussing a very important topic in waves, basically related to the standing of waves on a straight string, normal modes in straight strings, within air columns in closed and open glass tubes, and beats. So, we might have heard the word beats very frequently in case of music industry. In music, there are beats, and the normal modes. Then we'll be discussing the terms like harmonics, overnotes. So those are the terms which comes in our music industry, and there are various music instruments which are based on the principle of producing standing wave, and we have various instruments like violin, then organ pipe. So in those cases, actually, sound wave is produced produced by vibrating the air column. So at various lengths, there is a hole, or some cases there will be a tapping point. By tapping those points, various kinds of frequencies will be produced by the music instruments, and those are very interesting to understand how it happens. So let us start our class today, start our learning. So here I have given you the definitions of the standing wave, just to recollect what we have learned in the previous classes. So when two identical waves of same amplitudes, frequency, traveling in opposite directions with the same speed along the same path superpose each other, a resultant wave will be produced. That resultant wave will contain nodes and antinodes. We have seen that, which does not travel in either direction, is called the stationary wave. So we had given a very common example, that is the straight string between two rigid support. If you just pluck it up and then leave it, there will be wave produced. It will go from this end and get reflected back, and then the reflected wave will be out of phase. So there will be standing wave produced. That is what we have seen. So this figure is not very correct and very neat, but we have already discussed, so I have not given a proper figure over here. So here, the point which we should remember or note is that there are two things, like conditions for, or the positions for nodes and antinodes. See, two traveling waves. If we take two traveling waves, A sine kx minus omega t, which is traveling along positive x direction, okay, and A sine kx plus positive omega 2, traveling along negative x direction. And according to the superposition principle, if you find out the amplitude of the a resultant wave by applying trigonometric identity, then what we get is this into sine omega t. So this is an expression for the standing wave. If we take these two traveling waves which are having same amplitude, same frequency, having same propagation constant, and but traveling in the opposite direction. So from here we had found out positions for, or conditions also you can say, position of nodes. Nodes means zero amplitude. This is amplitude term. It will be zero when x will be n, see kx will be n pi by 2. Okay, so from here we can write this k as 2 pi by lambda. 2 pi by lambda, pi goes up, so we get condition for nodes to be x is equal to n lambda by 2. X is equal to n lambda by 2. So this is the condition for nodes. Okay, similarly when this is maximum, there we will get antinodes. So from there we can find out that condition for finding or positions of antinodes. Nodes are denoted by n, as you have seen earlier also. Antinodes are denoted by a. So position of the antinodes will be 2n plus 1 lambda by 4. That means odd lambda by 4. So these two conditions we will keep in our mind and try to analyze standing waves created in straight string, in the air column, in a closed pipe or tube, glass tube, and in open glass tube. So this is, here we are trying to analyze the various frequencies or the modes, natural frequencies produced in straight string. Let us see. Suppose this is a string having length L. Okay, having length L. Suppose here x is equal to 0 and here x is equal to L. All right. So since these 2 points are rigidly fastened, okay, fastened, if a wave travels like this, after coming from here, actually at this end, it will be reflected back, but with pi phase difference. Okay, phase difference, 180-degree phase difference will be there. Because this is rigid point, it will not, see here the medium particle will not move along with the wave. So that's why there will be nodes at the two ends. Nodes at the two ends, because the two waves, the original wave and the reflected wave, they will actually interfere in opposite phase. Therefore, there will be standing wave created, and standing wave consists of nodes and antinodes in this length. Okay, and at various points there will be, see, at some element of the string there will be no displacement, and at some places there will be maximum displacement. These are called nodes and antinodes. All right, so we know the condition for antinodes. Now we'll try to find out what are the, see, once you pluck this string, there can be a various number of frequencies vibrated. So various numbers of frequencies or standing waves may be produced in the string, and all those frequencies are called natural frequencies or modes of vibration. We'll try to find out the modes of vibration. That means various natural frequencies which could be excited in a string. So since at the both ends there could be nodes, so therefore this n points should satisfy. That means L should satisfy the condition n lambda by 2. Okay, at this end there should be a node. So look, this expression is telling you that there will be limited number of limited wavelength or limit in wavelength, limited in wavelength, because see the length L does not change. L does not change, that is fixed. That's why, see, if I say n is equal to 1, so in that case L is equal to 2, lambda is equal to 2L. That means within the L there will be half of the wavelength. Half of the wavelength means there will be two nodes at the ends and antinode in the middle. Look this one. So there are two nodes, and two nodes are separated by, we have seen two nodes are separated by lambda by 2. That we have seen in the earlier cases also. Okay, if I write, so this is actually related to one type of vibration or one particular frequency of vibration. If I write L is equal to n is equal to 2, then it is L is equal to lambda. That means within L there should be a complete wave. This is the complete wave. Okay, so complete wave means standing wave here, so there should be from the opposite side also. Look, this is the one. Like that we can have various frequencies or harmonics produced over here. So each wavelength will be corresponding to their different frequencies. We will just come to that. Look, we have got L is equal to this, and obviously if we want we can find out lambda from here in terms of L. So lambda will be 2L by n. So this is suppose equation number 1. Now what we can do, we know speed of sound is equal to, or speed of any wave is equal to nu and lambda. So from here we can find out what is nu. Nu will be v by lambda. What is lambda? Lambda is 2L by n. So this is in the denominator. So n will go in the numerator. So what we get, nu is equal to, I'll just remove things. So nu is 2v by, nv by 2L. I can just keep these two things here. See, this n is actually an integer number. It starts from 1, 2, 3, and it goes up to n. Okay, a large number. Okay. So what does this mean? This means various numbers of frequencies or various type of vibrations can be excited in the stretch string. Now, if you remember, the speed of wave, standing wave in, not standing wave, speed of traveling wave, transverse wave in string is given by root over T by M. What is T? If the tension in the string is T and mass per unit length is M. If the tension in the string is T and m is the mass per unit length, then we can just write this expression for frequency n by 2L into root over T by m. So this is the expression for the frequencies which can be obtained in a straight string. Look here, if we put n is equal to 1, so this I can write in general nu n. So I get 1 by 2L root over T by m. Okay, if I write nu is equal nu 2, that means in place of n we'll be putting 2, then we'll get this. And look, this is actually 2 into nu 1. Similarly, we can find out nu 3 is equal to 3 into nu 1. You can just try and see. And suppose nu 10 will be is equal to 10 into nu 1. So we are seeing that there could be various frequencies excited. Various standing waves can be produced in the straight string, and there could be various frequencies or many frequencies, okay, many frequencies corresponding to those standing waves, and these frequencies are actually natural frequencies for this straight string, and these natural frequencies are called normal modes, okay. And the lowest frequency nu 1, see, this is the lowest frequency, this is called fundamental frequency. Okay, we'll just go here. So we have seen nu 1 is 1 by 2L root over T by m. Then we have nu 2 is equal to 2 into nu 1. Then nu 3 will be 3 into nu 1. Like that, we are getting the integral multiple of nu 1. So these are called actually harmonics. These are called harmonics. Various frequencies are actually called harmonics. So this is the fundamental lowest frequency. Lowest frequency is called fundamental mode or fast harmonics. All are called harmonic, okay, all are called harmonic. So since the second nu 2 is nu 2 is twice of the first harmonics or fundamental mode, then this nu 2 is called second harmonic, okay, or first over note, second harmonic, or first over tone, not note, first over tone. And see, similarly, in case of any music instruments, there could be much more than one frequencies at a time. Okay, we'll see when we discuss the sound various normal modes in a open and closed glass tube. So I hope you have understood what is called normal modes. Normal modes are the natural frequencies with which string can vibrate. Okay, string can vibrate. So these are natural frequencies, mu1, mu2, mu3, like that. So they have been given special names, like first one, the lowest frequency is given the name of fundamental mode. Okay, and or it is called first harmonic. The nu2, which is twice of having frequency, nu2 is twice of nu1, so that's why it is called second harmonics, and nu3 is called third harmonics. Like that it goes. Okay, so there will be all the harmonics produced, but in the vibration of string it depends which harmonics will be there depending on our plucking point. Okay, plucking point or striking point where we strike on the string, depending on that various uh, frequencies will be available in the vibration. And one more thing is that, see, these various frequencies are together called harmonic series. Harmonic series. Okay, here we have to note one thing, that the let us take the fundamental frequency itself. So there is a law called, so this is, so there could be a question sometime, state the laws of vibration of the straight string. Laws of vibration of the straight string. Straight string. Okay, so what is the law of, like, what are the laws? So there are actually three laws. If you see, laws of length, laws of tension, laws of mass per unit length, or laws of mass. So there are three laws of vibration of straight string. First is law of length. So as I said, law of length, here see the fundamental frequency is, fundamental frequency, suppose we write nu, is inversely proportional to the length of the string. So the fundamental frequency of vibrating string is inversely proportional to its length if the tension in the string and mass per unit length are fixed. Okay, now there is a law of tension. So in this case we can see the nu is directly proportional to the square root of tension when the length of the string and mass per unit length of the string are fixed. So this is the law of tension. The fundamental frequency of a vibrating string is proportional to the square root of its tension if its length and the mass per unit length remains the same or fixed. Okay, now third law is law of mass. So here you can see this is nu, the fundamental frequency in the vibrating string is directly, not directly, it is inversely proportional to the square root of the mass per unit length of the string, provided T and L, tension and length of the strings, string are fixed. So these are three laws of vibration of the string, state string. These laws can be again modified if the rho, the density of the string and the diameter of the string in some cases is given. So in that case, look, if the okay, let us be here. So we know the laws of, from here we can write 1 by 2L root over T by M. We know this is the fundamental frequency. So we know the laws. Now if the rho, the density of the string, and capital D, suppose the diameter of the string is given. If the diameter of the string is given, then the mass per unit length can be written in different way. Okay, so this is volume of unit length into the density. Okay, so this could be written as pi d square by 4 into rho. So if we put this here in this, suppose this is equation number 1, equation number 3. So we have got equation 1, 2. This is 3. So nu here 1 by 2L will be there. T will be there. Here in place of M we can write this d square by 4 into rho. Okay. So look here, if we do little bit of simplification, then we'll get 1 by LT, 1 by L into D. Oh, sorry. 1 over LD square root of TY pi into rho. Okay, pi into rho. So then the law of vibration of the strings will be modified to nu that inversely proportional to L, nu inversely, or the frequency is inversely proportional to the diameter, and it is directly proportional to root T, and it is inversely proportional to the root over 1 by, sorry, inversely proportional to the density. So this is how the law of density and law of diameter will come along with the other. Okay, all right, along with the length. So tension is anyway there. So this is not new, this is also not new, only these two new rules will come, law will come. All right, we have thus completed the standing waves and normal modes in state string. Now we'll see how and which are the normal modes we see in a glass tube with one end open. So this is actually called as closed pipe. When one end is open, that is called closed pipe. Look here, the figure. See there, this is closed pipe or closed tube. So this is a glass tube where there is a water or some liquid filled in this. Since it is empty, there was air column within this. So there will be air column, and if you bring a tuning fork and just make some sound vibrations, that sound vibration will produce vibration in the air column. Okay, so that air column, and sometimes see we in our whistle, in the whistle also the same thing is done. Just blowing the air, we produce frequencies. Okay, various modes of frequencies we can excite. We'll see which are the harmonics produced in this closed pipe. Okay, so when we just put or like pour some water, so this end, look, this end will act as the close end. This end will act as the close end. Okay, that means what? The air column over here, when the sound wave is vibrated, sound wave means there will be rarefaction and compression. So in that case, at these places, the pressure change will be the maximum. Change in the pressure will be maximum, and hence there will be nodes produced over here. Nodes will be produced at this closed end. We have seen that when some wave is reflected at the closed end or rigid end, there the reflected wave will be produced with a phase change of pi or 180-degree out of phase. Original wave and the reflected wave upon superposition will produce standing waves, and at the closed end there will be obviously nodes. See, just by changing the level of the water, we can change the length of the air column. Change the length of the air column. Okay. But suppose we have a fixed length of the air column up to here to here. Suppose the length of the air column is some L. Okay. Some L is the length of the air column within this. And the air column is vibrated to produce some frequencies. So as we have seen, suppose this is x is equal to 0 and it is x is equal to L over here. So at this position there will be antinodes where at x is equal to L. So the condition for antinodes is 2n plus 1 lambda by 4, if you remember correctly. Okay, this is the condition for antinodes. So L has to satisfy 2n plus 1 lambda by 4. Now if we put L is equal to 1, sorry, n is equal to 1, look, we'll get L is equal to, sorry, here actually n starts from 0, 1, 2, 3, etc. It starts from 1, sorry, 0. So if we put 0, then we get the fundamental wavelength or fundamental wave produced in the air column. So n is equal to 0 means we'll get lambda by 4. That means, look, within this length of the air column, you should have 1/4 or 1/4 of the wave produced. Look here in the figure. So this is actually the fundamental mode of the first harmonic, where you will see within this length of the air column only a quarter of the wave okay. See, this is node and this is antinode. So the distance between node and antinode is actually lambda by 4. See, two nodes or antinodes are separated by separated by a distance lambda by 4. Okay, and another point is nodes and antinodes. A pair of node and antinode are separated by I'm sorry, this is lambda by 2. This is lambda by 2. Separated by lambda by 4. So this is what we have already discussed. So actually, if you have a web like this, suppose a standing web, then see this is antinode, this is antinode, this is antinode, this is node, this is node, this is node, again this is also node. Okay, look, this node and this node and this node, you look up to here. Okay, so when you have two nodes, leave the first point or starting point. If you have two nodes and two antinodes, that actually constitute a complete wave. That constitutes a complete wave. So this is actually a half of the wave. In between two nodes, this is lambda by 2. Okay, that you can understand. Okay, but up to here, if you have this and this, so you have like this. So this is the half of the node antinode itself. So half of the antinode means somewhere there will be another node here. Sorry, this is, let me draw this. Yes. So if this is the half, somewhere there will be another node here. So up to this is lambda by 4 and this is lambda by 4. So this two will actually give, because in between two nodes it will be lambda by 2. So this is actually lambda by 4. So if I just check with this is lambda by 4. This is actually lambda by 2 because two nodes are there. Okay, so now if we check with this is lambda by 4, this is lambda by 2, this is lambda by 2. Okay, this is how things are. Now we'll try to understand from here. So for the first mode, we have seen within this length there should be a quarter of the wavelength, of the wavelength of the wave produced in the A column. If I just put n is equal to 1, so it was actually n is equal to 0. So n is equal to 1 means the third harmonics. Look, why third harmonics? We will say as time comes. So here, when we put n is equal to 1, it will give you 3 into lambda by 4. 3 into lambda by 4 means, say lambda by 4, lambda by 4, lambda by 4. So or we can say lambda by 2 plus lambda by 4. Okay, this will give you 3 lambda by 4. Okay, lambda by 2 plus lambda by 4. Look this one here, within this length L, within the same length L, when the third harmonics is produced in the A column, you will see one half wave, half of the wavelength, and another quarter of the wavelength. See, this is the half of the wavelength. That means you have, see, this is node, this is antinode, this is node, and this is again antinode. So you have two nodes and one antinode. Sorry, two nodes and two antinode. Okay, two antinode. All right. So like that, if you go with n is equal to 2, then you will get the fifth 5 into lambda by 4. 5 into lambda by 4. This is what you will get. That means you should have lambda, total lambda plus lambda by 4. This will give you 5 lambda by 4. Okay, 5 lambda by 4. So lambda, that means you will have a complete wave along with a quarter of the node. See, quarter of the wave. So this is lambda by 4 and this is a complete wave from here. There are 3 nodes, 1, 2 and 3. 3 nodes, in between there will be 2 antinodes. Okay, this will, so for a complete wave there will be 3 antinodes and in between them there will be 2 nodes. Sorry, just opposite. There are 3 nodes and in between there will be 2 antinodes for a complete wave. Okay, I'll just clean everything. Now I'll go with frequency. So I have got 2n plus 1 lambda by 4. Okay, so in this case, if I just write L is equal to what? L will be 4, sorry, lambda will be 4L by 2n plus 1. Okay, this is the 1. Okay, so again, we know the speed of the traveling wave in case of air column is given by gamma is equal to, sorry, V is equal to gamma P by rho. Gamma P by rho. Rho is the density, gamma is, you know, that is the ratio of molar specific heat at constant pressure to the molar specific heat at constant volume, Cp by Cv, and P is the pressure in the air column. At various points, when the sound wave, that is actually longitudinal wave, so there will be rarefaction and compression while wave travels through the air column. Okay, sound wave travels through the air column. Now we'll try to find out the frequency. Expression for the frequency, we know frequency will be V, the speed, by lambda. So we have got the expression for the speed is this, and lambda is actually 4L by, so sorry, lambda is down like in the denominator, so we'll write here 2n plus 1 by 4L. This is the factor along with the speed gamma P plus, divided by rho. So this is the expression for the frequency. Look here, I'll rewrite 2n plus 1 by 4L square root of gamma P by rho. Now see, if I put n is equal to 0, then we get the fundamental frequency or the lowest frequency of the waves produced in the air column. So what is the lowest frequency? N is equal to 0 means 1 by 4L gamma P by rho. Okay, now if we put, so this is new 1. If we put n is equal to 2, then what we get? Actually we get new 3. N is equal to, so 3 by 4L root over gamma P by rho. What this is? This is actually 3 into new 1. Okay, now if we put n is equal to 2, then we get new 5. So here there will be 5 divided by 4L along with gamma P by rho. So this should give 5 into new 1. So this is the lowest frequency new 1, which is called the fundamental frequency, which can be excited in a closed pipe. This is called closed pipe. When one side is closed, that is called closed pipe. So in case of various organ pipes, we see this kind of frequencies produced. So these are called various harmonics. These are called harmonics. These natural frequencies are called normal modes or various harmonics. See, the fundamental frequency or the lowest frequency is called the first harmonic. So first harmonic has the lowest frequency, And see, as we go along, if we just put n is equal to 1, n is equal to 1, we get the third harmonics. That means the frequency we get putting n is equal to 1 is 3 times of the fundamental frequency. That's why, since it is integral multiple of the, so all the higher harmonics you will see, not all, here the harmonics we get are the odd harmonics we will get. So higher harmonics will be the odd harmonics. Higher harmonics produced in closed pipe are odd harmonics. Sorry, odd harmonics. Odd harmonics. So what are those? Like fundamental frequencies, or for the first harmonics we get third harmonics, okay, and then we get fifth harmonics. Like that, if you go, you'll get seventh harmonics. So these are all odd harmonics. So in a closed pipe, what we get the odd harmonics. So here you have to remember what is the frequency, fundamental frequency, and then what are the frequencies we obtain. Here we get odd harmonics. All right, we get odd harmonics in the closed pipe. Now we'll see what happens in case of open pipe. What happens in case of open pipe? So normal modes in a tube with two ends open. Two ends open, as you might be remembering. So this is called open pipe when both the ends are open. Okay, like float, various kind of floats, or yes, so various kind of floats. So both ends are open. So when both ends are open, actually at the end points there will be antinodes, as you see, and the middle there will be nodes. Each and every cases, whatever modes of vibrations it may be, at the ends there should be antinodes. Okay, and since antinodes at both the points, both the ends, so we can write this as okay, so we can actually see that the all harmonics are produced here. Actually, in this case, at any point you take, so you will get actually antinodes. So L can be written as, or the frequency itself I can directly write the fundamental frequency what we get in this case. Let me write this n lambda by 2. Okay, n lambda by 2. We get n lambda by 2. This is the condition for antinodes at one end. So we can look here by putting n is equal to 1, 2, etc. So how, like within this length L, within the length L, how many wavelengths or how much of the wavelength could be there? So suppose L is equal to 1, sorry, n is equal to 1, then we get lambda by 2. What does this mean? N is equal to 1 means first harmonics. So a lambda 1, suppose lambda 1. So you have actually half of the wavelength. So half of the wavelength means, see, this is lambda by 4. This is antinode. This is antinode lambda by 4. So this is with the first harmonics, or the fundamental frequencies. Okay, or the wave with fundamental frequency. So this, if you add, you will get lambda by 2. Then n is equal to 2. That means L is equal to lambda. So this will be second harmonics. Okay, this is first. Second harmonics should actually show a complete wave within the length. So complete wave means, see here in this case second harmonics, this is lambda by 4, this is lambda by 4 because at the open end there should be antinodes, and this is lambda by 2. There are two nodes, so this is two nodes are separated by lambda by 2. So you look, this is actually lambda by 4 plus lambda by 4 and lambda by 2. So you'll get lambda. So within this length there should be a complete wave. And see, this complete wave actually is denoted by its nodes and antinodes. So there should be three antinodes and two nodes in this case. Okay. Similarly, third harmonics, fourth harmonics, in this case, all the harmonics will be present. So in open pipe, all harmonics will be present. All harmonics will be present. So you can just note one thing, that when all the harmonics are present, then the quality of the sound in case of open pipe would be much more than the quality of the sound in closed pipe. Okay, so the quality of the sound depends on the number of harmonics present in that sound. So in open pipe there are all the harmonics excited in this air column, so this quality of the sound will be much better than that of the closed pipe. Now we'll go for the expression for the frequencies. So from here we'll find out the lambda will be 2L by N, and from there we know we can find out nu is equal to speed of the sound or speed of longitudinal wave within the air column divided by lambda. Lambda is actually 2L and N goes up in the numerator. And anyway, within the air column, the speed can be written as again root over gamma p by rho. Gamma p by rho, I have explained what is rho. Rho is the density of the air column. Okay, and p is the pressure, and gamma, that is the ratio of the molar specific heat at constant pressure to the constant volume. Now see, fundamental frequency when n is equal to 1. Here actually n starts with n is equal to 1, 2, 3, etc. Okay. Now new fundamental frequency, or the first, this is actually called first harmonic. Now you look, n is equal to 2 means this will be 2 nu 1, then nu 3, that means n is equal to 3, so this will give you 3 into nu 1. So these are actually integral multiple of the fundamental frequency. So all higher harmonics you will get 1 is the fundamental, then 2, 3, 4, 5, all you will get. So that's why you'll get all the harmonics in open pipe. Okay, now we'll just okay, so another 5 minutes we'll conclude the class. 5 to 6 minutes. I'll just discuss about bits now, so that our class will be completed for this topics. So see, when two sounds of slightly different frequencies traveling along the same path and in the same direction in a medium, if they superpose, then upon superposition, the intensity of the resultant sound at any point in the medium rises or falls alternately with time. So what is the case? Look this. So there are actually two sound waves. If you can look, there are two colors. Suppose two sound waves. Okay, one is this orange, or maybe you can say red. This is blue. So there are two frequencies, nu1 and nu2. They are having same amplitude, same frequency, etc. Sorry, not same frequency, slightly different frequency, same amplitude, and they are traveling in the same direction within the same medium. And in this process, if they superpose each other, then what happens? The resultant wave, the intensity of the resultant wave, that means the amplitude of the resultant wave. Intensity means what? Amplitude square. That means the amplitude of the resultant wave will actually rise or fall. See, this is the point where it is rising, the amplitude. Okay, and this is the point where the amplitude is actually falling. So this is the thing will be created when, if there are two sound waves of slightly differing frequency. Suppose 705 hertz, one frequency, and another frequency is 706 hertz. So there is a very slight difference. You can see that. Or let us take, this is 5, this 710, let us take. This is 710. If they superpose each other, the intensity of the sound wave, intensity, since the amplitude is changing, like rising and falling, and this will be periodic. It is very, very interesting to see that it will be periodic. Obviously, the frequency of this rise and fall, or the time period of rise and fall, will be different. Will have different time period and frequency than the original waves. Okay, so that's what we can see here. See, this rise, consecutive rise and fall, actually together, one rise and one fall together constitute a beat, constitute a pair of rise and fall of intensity, actually called beat. Okay, we'll define. So let us write the definition. Okay, let us write the definition. So when two sound waves, two sound waves of slightly, sorry, when two sound waves of slightly differing frequency, slightly differing frequencies, frequencies traveling along same traveling along same path in the same direction of a medium of a medium superpose, sorry, superpose then the resultant sound at any point of the medium, resultant sound at any point of the medium will periodically rise. Resultant sound at any point in the medium. So then the intensity of the resultant sound, intensity of the resultant sound at any point will periodically rises and falls. Okay, these periodic vibrations that means waxing and waning. Waxing means rising, vibrations, this periodic vibrations, waxing, that means waxing and waning, waxing and waning of intensity of sound waves sound are called beats. Okay, so these periodic vibrations in the intensity of sound caused by superposition of two sound waves of slightly different frequencies are called beats. So one rise and one fall of intensity constitute a beat. One rise and one fall. See this is a beat. One rise from here, okay, one rise up to here, one fall. So this constitute a beat. Okay, this constitute a beat, and this beat actually is vibrating with the frequency. So that is called beat frequency. What is the beat frequency? Beat frequency is obtained by taking the difference. Suppose one has frequency nu 1 and another one has frequency nu 2. So the beat frequency will be difference between the two frequencies. Okay, if I take an example, suppose nu 1 is, as I was taking, this much hertz, or let me write 750 hertz, and nu 2 is 7, not 10, it should be nearly, so suppose 760 hertz. This is at the margin anyway. Let me take it 57 hertz, 757 hertz. Okay, so the bit frequency in this case, bit frequency will be 7 hertz. Okay, just take the difference. Okay, now see what are the essential conditions for bit to happen. See, this is actually, let me show you here. If you don't understand what is maximum or what is minimum, see the sound is actually, this is a bit period, this time This is actually bit period, one rising and one lowering of intensities. Okay, so let me just write the bit frequencies over here. Bit frequency, bit frequency. Bit frequency is nu 2, nu 1. Difference of the frequencies. So then what will be the time period of bit? Bit period will be t is equal to 1 by bit frequency, right? 1 over bit frequency. Bit frequency. 1 over bit frequency. All right? It will be 1 over bit frequency. If you know the bit frequency, then you can find out bit period. All right, so next day, I will actually discuss in detail, little bit more detail, how we are getting this waxing and waning of intensity. Mathematically, I'll prove this, and we'll take up practical applications of these bits in the next class. Practical applications of bits and how this bit is actually produced. Okay, and actually you can see that the beat is actually vibrating with a particular frequency that is called that is called the envelope or the modulation of the frequencies. See, these are frequencies, these are rapidly vibrating and this is slow vibrating frequency. So those things, those intricate things we'll discuss in the next class. Okay, so this is kind of overlap which I'm drawing. So that is having a lower frequency than the vibration you see. So this has greater frequency, you see here. So here the frequency will be nu 1 plus nu 2 by 2, the average frequency, and this will be modulus frequency, that means nu 2 minus nu 1 by 2. Okay, so those things we'll discuss mathematically in the next class, and we'll see what are the applications of these bits. Okay, thank you for your patience. Bye for today.